So I want you to, I've got a few things I want to get out of the way first, and then I want to, is that way too loud? If it's too loud, let me know, I'll turn it down. Um, but you're going to need that in a few minutes. So one of the things I wanted to go over with you was, I was missing the other day, that um, in a house, they use in a household circuit, they use the secondary voltage, which is, here's your primary voltage coming in. Your secondary voltage is this center tapped, and this is 120, this is 120, and from here to here is 240. Okay, that's a household circuit. And that's how you use 110 in a residential, but in a industrial application, I told you you only had one 110 and not multiple ones. So what you actually have is, and this is usually 440 or whatever. I don't know what this is, but I don't know what the voltage is outside. But anyway, whatever it is, in a industrial application, this is 440 or whatever, and this is, there's fuses here, and there's a fuse here. This goes to ground. This is 120. 480 and 120. It should be 480 and 120. But anyway, that's it. You do not have multiple sources, and you don't have 220. And this is all you have in an industrial application. So if you're looking at the two and why, I told you why they don't have the 220, because if you're grabbing a hot wire, um, you're if you grab a hot wire, you want it to be the only hot wire in your panel, and that's this wire right here. You do not want to have multiples. And if you do grab, if you do have multiple sources, they should be yellow wire. So if you have another source, it should be from another panel. So in your panel, you should only have one source, and that would be this one right here. Okay. So now we're gonna. I I've been obviously I've been struggling, but now I'm going to do something a little different, and we're going to go with. Okay, I said that. So this is a video, and I'm going to play it, but I'm going to stop it from time to time, and we're going to do the calculations ourselves. So basically, this is a.
My name is Dan Carnevale. I'm the director of Eaton's Experience Centers here in Pittsburgh and in Houston, Texas.
Is that too loud?
And I welcome you today to this session. This is on basically rules of thumb and calculations that you'd like to know for doing consulting work in the power systems field. So we're going to talk about transformer calculations, fault current calculations, and so forth. So the purpose and learning of this event or this session is really to gain a good understanding of the key power system concepts and calculations that apply, and basically around rules of thumb. So if you're thinking about the person sitting next to you that's been in their job for a long time, we want you to understand how do they come up with these calculations. At the end of this presentation, you'll be able to size transformers, cables, and protective devices based on the three-phase calculations. And also to be able to understand the calculations for motor starting, power factor correction, and three-phase power. Engineers love to write on things. Pick a napkin, maybe at the back of an envelope, as people always say. Or one night when I was sitting at my kitchen table with my son, who's in engineering school, we were writing on the back of a pizza box. And it reminded me of the fact that engineers love to draw and love to do these calculations to think things through. And so to me, having the capability to come up with those numbers on the fly is important. And as an engineer, you need to understand where those equations come from and how to use them quickly and correctly to get you the right answers. In this session, we'll talk about three-phase calculations. So we're going to simplify it to those calculations that are appropriate for three-phase. There will be one or two that are single-phase, but we'll talk about those when they come along. The one thing that's important is really kVA. That's the main equation that we're going to use from the simple calculations of kVA, including voltage and current, and the square root of 3 were appropriate. We're going to talk about full load amps. How do you size the circuit breaker that comes into a transformer, or goes out of a transformer, or goes into a panel board or switchboard? And then how do we calculate fault current? And where do we calculate fault current? Breaker sizes and Ka ratings for that fault current. And then motor starting and load calculations. The power triangle, one of my favorite things to talk about. Kilowatts, kVAR, and kVA. And then power factor correction. And how do we use a one-line diagram to get all that information and put it together? Okay, so when do we use the square root of 3, the square root of 2, or the square root of 1? The square root of 3 is when we have three-phase calculations. Now, most people think that volts times amps equals watts, and we know that that's not true in AC power systems. Volts times amps equals volt amps, or kV times amps equals kVA. So when we have single-phase power, we say kV line to neutral times I line equals VA, kVA, single phase. If we multiply that by 3, we get the three-phase equivalent for a balanced system. Now, the square root of 3 comes into play when we have kV line to line, because kV line to line versus kV line to neutral is off by the square root of 3. kV line to neutral times the square root of 3 is the same as kV line to line. So when we have our typical three-phase power calculation, we're going to say kVA, three-phase, equals the square root of 3 times kVA line to line times the current. And that's going to be the equation that we're going to use a lot for the rest of the calculations for our transformers. When does the square root of 2 come into play? That really comes into play when we're talking about the RMS versus peak. Now, if you look at the peak and you compare that to the RMS, which is more of an average value, it's typically off by the square root of 2 when you have a very nice sinusoidal waveform. Where that doesn't happen is when you have harmonics, like the bottom picture, where the current has a crest factor or a peak over the square root of, or a peak over the RMS of maybe 3, or a number considerably higher than the square root of 2. So the square root of 2 comes into play for those kind of things, and as a consultant, you might not run into that as much unless you're dealing with waveforms and harmonics and things like that. But the square root of 3 will be all around, and if you understand those equations on the left, that's going to be a big deal if you can understand the square root of 3. Square root of 1 you can use for everything else. So as a consultant, why do you need a one-line diagram like this one? Well, it's really important. If you're going to try to do calculations, you really need to have a good understanding of the actual numbers of values for the equipment. And there's two things associated with that that are important. One is you don't always immediately trust the one line. You have to make sure that it's accurate. But the second thing is really to make sure that you have all the data that's on the one line that matches up with your equipment. So sometimes you have to field verify, again, through nameplates on equipment and so forth. But if we have the one line, like in this case, we can calculate and we can use the utility source impedance, the utility main breaker, substation transformer, medium voltage switchgear, like we show in the middle, unit substation transformer, for example, and then low voltage switchgear or switchboards, and then multi-case breakers and dry type transformers down through the system. So all of that equipment with its proper information on the one line is going to be super helpful to doing your fault analysis and your load flow calculations and all of the things you'll do as an engineer or consultant. Now what we're going to do is we're actually going to go through and calculate full load amps on the primary and secondary of a transformer, the fault current on the secondary, and also the breaker or fuse size and the Ka rating of those breakers. We're going to talk about how that comes into play here. Now, I'm going to actually take you for a walk and show you a couple of these transformers so you can physically see what they look like, because they're not just squiggly lines on a piece of paper. They're actually physical devices. And I'll show you the difference between the liquid-filled ones and the dry types and the pole-mounted ones and the things you're going to have in your one-line diagrams that won't necessarily correspond to something physical you've seen before. And I think that's really important to see how that all comes together.
So to get to the calculations that we need for a transformer like this, we want to think about full load amps on the primary, full load amps on the secondary, breaker sizing for primary and secondary, and then also fault current on the secondary. How are we going to get that information? Well, what we're going to do is we're going to go up to the nameplates of these transformers, and we're going to find out the information that we're going to need to plug into our equations to calculate those values. So let's take a look at some actual transformers and see the ones that we're going to use in our calculations. This is the first one. This is a dry type transformer, 75 kVA, 480 volts in, 208, 120 out, and it happens to be a K13 transformer, delta Y. So this next transformer is a little bit unique. We call it an isolation transformer. And what does that mean? That means the voltage on the input and output are the same. So we're just using it to reestablish a ground system through the delta Y and the Y connection on the secondary. This one happens to be 460 in, 460 out, 550 kVA. It's also connected, in this case, not solidly grounded, but to our high resistance ground system, which allows us to have one free ground fault. And you might use that on an industrial situation, for example. Now here's a transformer on a pole. We can see it's single phase. It's 13,800 volts on the input and 240, 120 coming into your house in the output. How are you going to figure out what size that one is? Well, we can see the 10 on there. What that means is 10 kVA. But the problem is, unless I climb that pole, I don't know what the transformer impedance is. So we're going to have to make some assumptions on this one. Hey, I'm up here. So these ones are a little different. Now, again, don't try this at home. I just happen to be up there because I know these aren't energized. But if you look at these transformers, it has 25 kVA. So three of them together make a bank in a delta Y configuration of 13,800 volts in this case to 480 volts, Y connected, so 480, 277. And this one's going to be solidly grounded. And I'm standing right up here next to the nameplate. So I'll show you a picture of the nameplate in the PowerPoint. But again, this is what you might see in front of like a strip mall. Now this is a 750 kVA pad mounted transformer. This thing's liquid filled or oil filled. And it's medium voltage on the input and 480, 277 on the output, for example, or it could be 208, 120 volt on the output. The interesting thing about this is without opening the doors, a lot of times you won't be able to see the nameplate. So sometimes they have written on the outside the kVA rating of these units as well from the utilities standpoint, so they know what size they are when they go to replace them if they fail. So this transformer is 5,000 kVA, but it also has a slash rating 6250. And that's because we have fans and radiators on the back to cool it down so the oil can move through those radiators and we get more kVA out of the transformer. That's going to come into our calculations for full load amps and also our fault current a little bit differently, so we have to think about that. This one has 34.5 kV in, 13.8 kV out.
Okay, so let's get into the fun stuff. Let's calculate the full load amps on the primary and secondary of the transformer.
Now, as you look at these, I counted 10 examples, so I divided them into 2 days. We're not going to go through all this today. We're going to go through half of it. And I'm going to stop, and you can do your calculations, or you can do some of your calculations as you see fit. You can also go back and you can do this later if you want to. So you don't have to do it right now. If you want to kind of rush through it and kind of get an answer, you can. I may, at some point of these, stop and do some of it myself. I'm not going to hurt myself to try to get them all done. But between you and me, and I haven't done these either, but basically I'm going to stop so you get a little bit of a chance to do some of these calculations yourself. But I'm asking you to change one number at the beginning of each one of these. You follow me? I'm asking you to change a number and then go through the calculations of that other number. Now, that doesn't mean that the number that I picked is an actual valid size of a transformer. It just means that I offset their number by some number so that we could have little different numbers we could talk about and make everybody calculate something out. But basically, there's 10 of them, and they're all different. So, I mean, you will never get a better example of, how many different ways you can calculate fault current in a transformer than this example, this video right here. And this isn't all of them, but this is just an example of some of them. So I'm going to shut up and let you, but if you want me to stop, I'll stop. I'm going to pick a point where I think it's ready to stop, but if you think you're ready to stop, raise your hand or whatever and say, now wait, we'll stop right here and we'll stop it and get is that okay?
Here, I full load on the primary. I full load on the secondary. three-phase fault current, I fault, three-phase here. And that's going to help us determine the wire sizes on the primary and secondary, as well as perhaps the breaker sizes here on the secondary and there on the primary. Now we're going to use the information from the transformer. So again, we're gathering information from the transformer's nameplate. Let's just use this as a very simple 1000 kVA, 13.8 kV primary to 480 volt secondary, impedance 5%. So we're going to go back to the equation that we started with, and we talked about for three-phase power, which is kVA three-phase equals square root of 3, there's a square root of 3, kV line to line times I line. So if we solve for the current, I line equals kVA three-phase divided by square root of 3 divided by kV line to line. Then we just substitute in if we're on the primary or the secondary to calculate our current. So for example, current I full load on the primary is 1000 kVA divided by the square root of 3 divided by 13.8 kV.
Good. Everybody got that? So far, so good? Everybody see that?
I think you can make the screen a little bit.
And so let's calculate that out. 1000 kVA divided by 1.73 divided by 13.8. And that works out to be about 42 amps. Okay. Now, if we want to look at the secondary current, I full load secondary, we would take 1000 kVA divided by the square root of 3 divided by 480, right? Well, here's what's going to get you in trouble. If you do that, 1000 divided by 1.73 divided by 480, your current is 1.2 amps. And if you have 1.2 amps on the secondary and 42 amps on the primary, you should know that something's wrong. And in fact, what you forgot is this is kV on the bottom, kV line to line on the bottom. So we have to do 0.48. So if we divide that or multiply that by 1000, we end up with the correct answer, which is 1204 amps. And
You got that?
one really cool thing about 480 volt systems is that if you take 1000 kVA, 1000, multiply it by 1.2, guess what? 1200 amps, 1204. So there's a good rule of thumb that basically says if you have full load amps on the secondary of if you have full load amps on a 480 volt system, it's about 1.2 times the kVA rating of the transformer. Now, let's take this to the next step, which is how do I calculate my fault current? So if I want to calculate my fault current, I three-phase fault, it's actually very simple. All we do is we take I three-phase full load amps secondary, divided by the impedance in per unit. And we'll talk about what that means. Basically, per unit at 5%, per unit is 0.05. So we take 1204 divided by 0.05, and we get
Got that? That's how you get full load. That's how you get your fault current.
$12.04, $12.04 divided by 0.05, and we get 24, about 24,080 amps, or 24 kA. That's our fault current. This number, since the impedance is 5% or 0.05, this number is 20 times the full load amps. Again, interesting things to think about. When you think about the impedance, 1 over 0.05 is about a ratio of 1 to 20. So the ratio of the full load amps to the fault current is 20 times. And that's how we're going to size our KA rating for our breakers. So those are just a few of the things that we want to think about. Now, on the next page, we're going to talk about the infinite bus and why do we not calculate the fault current on the primary side. The reason we can't is we don't know what the impedance back here is. So let's talk a little bit about that. So what does an infinite bus mean? An infinite bus basically says that we have zero impedance all the way looking back to the source. And we know that's not exactly true. Of course it's not true. But if it's low enough, the calculations work out so that we can actually ignore the fault or ignore the impedance of the upstream transformers and cables and everything else, and just use the nearest upstream transformer as our main source impedance. That becomes especially important when you're doing things like fault calculations and even harmonic analysis, really, to be honest with you, for resonance and things like that. So if you can understand transformer impedances and you can calculate all that, then you can figure out, how that comes together. How much of a difference is it? It's usually less than 5%. And in fact, it actually errs on the conservative side. So if we ignore that impedance, what are we doing? We're making the impedance lower. If the impedance is lower, our fault current is going to be higher. So actually it makes, for a better or a more conservative calculation. Now, what if our per unit voltage is not 480 or 13.8 kV, but maybe 5% high? Again, we have to think about that. So we may actually add in a little bit of fault current into our final calculations. Okay, so I showed you a few transformers earlier. Let's start to do some of those calculations that we talked about. So again, we're going to try to look for primary and secondary full load amps and secondary fault current. Now, here's the transformer, here's the inside of it, and typically you're not going to get to see it with a nameplate, with the cover off of it. So what we usually do is we walk up to the nameplate and we start to gather the information that's on the nameplate. What are we looking for? kVA rating. We're looking for primary voltage, secondary voltage. Sometimes we worry about the configuration if it's delta Y or delta delta, for example. But for these calculations that we're going to do, it honestly doesn't matter for that particular part. And then we also look for impedance, and that's the Z value that's on the transformer. Okay, so let's start in with fun stuff with the actual transformers that we saw in the PQ lab here. This is one of my favorites, and you'll see why in a minute. It's 75 kVA, K13.
You got all that written down. Instead of 75, it's an 8. We do it in 80. We're doing it a little different so that you get different numbers. But basically, it's the same thing. Everybody got that written down?
So on the homework, are you asking us to do the calculation on the 100 kVA and then the 125 kVA or just the 125?
Just the 125. The homework is to do another number. It's they did it one, we do it another. But basically, just run through the calculations because I don't know what we're going to do for a midterm test. But whatever it is, you'll have sheets that you can bring with you. You don't have to memorize any of this stuff. If we do it as a take home, I'm not sure you'll have that as well. But basically, all you have here is his verbiage on the video, so you can do the calculation. Yes. The first one was 100, wasn't it? 1,000. So I got go to 1250. I'm sorry. Yeah, I went through this in a real hurry. So yeah, go to 1250. Yeah. There's another one I saw that was missed as well. Yeah, it's 1,000 to 1250. Yeah, sorry about that. Yeah. I'll get these right. I did these about 20, the paint is still wet on these. I did this about 20 minutes ago. I was, I, honest to goodness, I'm barely sliding into the tag, under the tag on these things. So you got, you know, by the time you get done with it, you'll be experts at calculating fault current. You'll have 10 examples, different ones of different types, so whatever.
13, which by the way, K13, TP1, HMT, all kinds of strange transformer names that might come up. That's not going to affect your calculations for these things that we're seeing here. It actually does affect the impedance of the transformer, things like that, when it's put together. But in fact, whatever's on the nameplate is what you need. So as far as that goes, this information on the nameplate is all you need. 480 volt, 208, 120. What does that mean? It's 480 line to line delta on the primary, 208 line to line on the secondary, connected in a Y, so 120 line to neutral. And the impedance is 4.262%. So let's calculate I full load primary. All right, so we go back to our equation we had before. I full load primary is going to be, in this case again, 75 kVA. So it's kVA divided by the square root of 3 divided by kV. And again, we got to make sure we use 0.48 here. So we take 75 divided by 1.73 divided by
Got that?
0.48. And we get 90 amps. Remember what I told you earlier? 75 times 1.2. Oops. Divided by 75 times 1.2 is 90 amps. So we end up with 90 amps, which is that 1.2 multiplier when you have a 480 volt system. Now here's the cool thing. If I want to calculate I full load secondary, I know it's 208 amps. How do I know that? Well, let's go ahead and multiply it out. 75 kVA divided by the square root of 3 divided by 0.208 volts, or kV, because it's 0.2, and we get 75 divided by 1.73 divided by 0.208, and that works out to be 208 amps. If you can remember that a 75 kVA 208 volt transformer gives you 208 amps, so 208 volts and 208 amps, what would be a 750 kVA transformer? Well, then it's 208 times 10, or 2080 amps. And again, that's just a side note. Again, rule of thumb, something to think about, something to remember in the back of your mind. And as I said in the previous page, what if it was 300 kVA? Well, if it was 300 kVA, it's 4 times this number. So an easy calculation for you to remember to do that. Now, so that's full load amps primary to secondary. What if I want to calculate my fault current here? I fault. So then earlier I mentioned we just divide the full load amps by the impedance, but really what we're doing is we're calculating kVA short circuit. And kVA short circuit is kVA full load, which is our rating or rated, divided by the impedance in per unit. So in this case, it's 75 divided by 0.0462, which is 75 divided by 0.0462. That's 1623 kVA. And then that number, if we use our I fault, three phase, we're going to take our short circuit kVA, which is 1623 kVA, divided by our square root of 3, and divided by our 0.208 volts, which is 208, and we end up with about 4,511 amps of fault current.
Already got that? So far, so good? I thought I'd do it slow so you could do it right in class, or if you want to do it later, you can. If you're tired and you don't want to do this, you can just come up later and do it. Or you can, if you want to do it now, you can. We're just going to do 5 of them, then we'll stop. I promise you, we won't do all 10. We'll do the other 5 tomorrow or next time.
If I took my number here that was 208 amps, I take 208, divide it by 0.0462, I end up with 4,502 amps, which is very close to that number. I just was off by basically the square root of 3 factor that works out in there. But anyway, this number, our full load amps and our fault kVA are important. And so you can see that we're using the same equation. We're using that same equation, which is kVA equals square root of 3 kV line to line times I line. And if that kVA is our fault kVA, which is what we used here, we can then calculate the fault current here. So the equations are all the same. It's either kVA full load or rated, or kVA fault. And the way you get kVA fault is divided by the impedance. But again, if you can remember that 208 volt and 208 amps, that's going to come in really handy. Now this transformer is a little bit unique. This is called an isolation transformer. And again, isolation transformers might be used in front of a motor drive as is shown here. The interesting thing about isolation is, again, it goes 480 in or 460 in this case and 460 out.
He has a stall.
Okay, for the next transformer, we have this unique isolation transformer. And again, it's 550 kVA, 460 volt rated in, 460 volt rated out.
Basic, third one down.
Five hundred or 5.12% impedance. Now we're probably going to apply this on a 480 volt system. So the bus voltage here is 480 volt, and the bus voltage here is 480 volt line to line. But how are we going to calculate the full load amps on the primary and secondary and calculate our fault current? So again, we'll start with our same equation we've been using the whole time here, which we're going to do I full load primary. And in this case, it's going to be the same as secondary, coincidentally, because the voltage is the same. It's going to be 550 kVA divided by square root of 3 kV line to line. Now, the tricky part is, do we use the rated value or do we use the actual applied voltage? And what I'm going to tell you here is let's do it both ways. Let's do 460. And then we're going to do the same thing, 550 kVA divided by square root of 3.48. And let's just see what the difference is there. So 550 divided by 1.7.
One.
3 divided by 0.460. Now that gives us our 691 amps. If we do the same thing, 550 divided by square root of 3 divided by 480, we get 662 amps. The windings and the actual transformer are designed to handle 691 amps. But what you have to remember is kVA is a capacity thing. It's volts and amps together. So if we run at a lower voltage, we could go up to that amp capacity rating. If we run at a higher voltage, we're likely going to only want to put up to that many amps through it. Otherwise, we're going to exceed the kVA rating of the transformer. So that's why these two numbers are important to understand. Most of the times, you'll see motors rated at 460. You'll see transformers rated at 460. A lot of times that's because they're down in the system where you expect the voltage to run somewhere near that level. And so to get the full load capacity out of them, you can use that 460 volt level. So anyway, again, sizing the breaker here, we might size it for 660. Well, it's not going to be exactly that. It's going to be something less or a factor of that, even a little bit more, depending on how our protection scheme is done. But we're going to typically base it on that because we know we're applying it at 480 volts. Now the fault current, I'm going to use that I fault is I'm going to use the short circuit kVA for this one. And the reason I'm going to use the short circuit kVA is because that's based on the rating. So, and then the kV line, we're going to divide that by the impedance. So we're going to do 550 divided by the square root of 3 divided by 0.46. And then that's our short circuit kVA divided by our impedance, which is 0.0512. So we get 550 divided by that. That's going to be that number.
Okay, we got it?
691 divided by 0.0512. And that's going to work out to be 13,496 amps. That's our fault current. And honestly, again, these are estimated values. So let's talk about that for a minute. If we have an estimated value of 13,496 amps, is it going to be that? No, absolutely not. It's going to be probably less than that. Why is it going to be less? Because remember, we ignored our primary impedance of our source above that. And a lot of times in this case, especially where you use an isolation transformer, the transformer upstream of this might not be very small or very big. In fact, it might be closer to the range of this transformer. So we do have to take that into account sometimes in a more formal study. But again, it's going to knock that number down. Also, if we have motor contribution here, that motor contribution could increase the fault current for a short period of time during fault conditions. So again, these numbers are estimates. If that number was 13,500 amps and you were putting 35 kA breakers in on this system, it's not going to matter. It's so different that it doesn't matter. If this number was 34,000 amps and we weren't exactly sure what the impedance up here was going to do and the motor contribution was going to do, I would be much more concerned. So again, using these estimated calculations, we can go through that and figure it out.
Is that number so as low, the breaker sizes usually are in the 40, 50, 60,000 range. That's why he's talking about that. That 13 is a lot less than 50 or 60. So that's what the breakers are usually rated for. So that's why he's talking about it like that. Anyway, hopefully some of this makes sense a little bit. And you're calculating of numbers that are actually meaningful.
Okay, now moving on to a different type of transformer. These are pole mounted transformers. And this is actually the kind of transformer that's going to be out in front of your house, for example. You either have this type of transformer or you have one that's pad mounted. But in the case of the size, it's usually 10 kVA, 25 kVA, and that's what we see on this one. 10 kVA, that's the number that's written on the side of the transformer. Okay, now this is a fun one because this is what's outside your house. And you want to think a little bit about what's the full load amps on the primary and secondary on this transformer. I didn't draw the secondary here because I want to show you something. This is 13.8, typically line to line, or it could be line to neutral, which is this number divided by the square root of 3. And so if we knew the primary voltage, let's say 13.8 kV, and we divide by the square root of 3, we would get 13.8 divided by 1.73, 7.97. So that would be our kV on the primary side, okay? But the way you can tell that is if you look at the transformer, and the transformer has 2 bushings that are about the same size. Typically, they feed them line to line. You'll see your secondary bushings coming out of the secondary here, and the 240 volt and the center tap neutral, grounded neutral is coming off there. If there's only one tall bushing and one short bushing, then a lot of times it's line to neutral. They do that because the cost of the bushing obviously adds to the many, many, many transformers that are out there. So sometimes they apply them at line to neutral rating, or in this case, line to ground, and sometimes apply it at line to line. But we're going to just say it's line to line for this one. The secondary of the transformer looks like this. This 2 windings coming off of there are 120 volt to a grounded neutral. So the neutral is grounded. It's brought into your home. And so it's 120 volt here, 120 volt here, and then 240 volt from here to here. So what are we going to calculate? The breaker that's in your home typically is a 2-pole breaker that's connected on that 240 volt line. So we're going to calculate based on the 240 volt. So instead of using that kVA 3-phase is equal to square root of 3 kV line to line times I line, we're just going to say kVA equals kV times current. In this case, we know the kVA.
Got that? So this is single phase.
What is the 13.8 kV?
That's the high voltage. That's the high, if you were to take the voltage across the primary that was coming into your house, but at the other side of the transformer, that's what the street voltage is. And that's why it's so dangerous, because that's high voltage, and that'll kill you in a heartbeat. It's out in the, if it falls onto the street, it's 13,000 volts, and that's typical. That's why it goes bzz, 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 or dances when you're whatever.
Which is written on the side of the transformer, 10 kVA. And then the voltage is either going to be 13.8, we said, on the primary. So that'll give us our I primary, full load. Or, and so let's just calculate that out. So we'd have 10 kVA. So I equals.
Said 10s or 25s. I said 15. There is no such thing as a 15. They go 10 and they go 25, but I just used it as a false number, just to, but I don't want to lead you astray and say there are 15s. I don't believe there are. They said 10s and 25s, but anyway, I just threw a number at you so that you would have to change the numbers and do it. But anyway.
I want to use my square root of 3 in there. I divided by voltage, so 13.8. So 10 divided by 13.8. And really right away we can see that's less than 1 amp, so 0.725 amps. So that's what's kind of cool if you think about it. They could use almost like an Ethernet cable to feed your house. It's very, very low gauge wire, but that's why they can use like a 10 or 12 gauge wire uninsulated in the air, just feeding the primary. And you're going to see that wire is small. It doesn't even need to be as big as it is, because you have less than an amp on the primary. The other part about this that's cool is if you look at the secondary, secondary full load, we have 10 kVA divided by 240, so 10 divided by 0.24, and we get about 42 amps, 41.67 amps. So for obvious reasons, then we put 200 amp panels in, or we put multiple 200 amp panels in our house, right? What's cool about this, when you think about it, our panel in our house is 200 amp, but we can only supply 41 amps or 42 amps from the utility transformer based on its capacity. But the utilities actually will push these transformers up even more, and they'll let you draw through maybe almost 2 times the normal KVA because they'll just let them blow off the poles. But the reality of it is you're never going to approach the 200 amp panel that's in your house. So why do we put 200 amp services in? Well, we don't know. If they have a 10 kVA transformer, they may upgrade that to a 25 kVA transformer or maybe 50 kVA. So we don't know. And so the capacity of the service coming into your house is what really dictates your breaker and not necessarily the full load amps in this case. Now, as far as the
Everybody get that? They don't supply, at a 10, they don't, that's all they give you is 41 amps. Anyway.
fault current, let's just take that number, 42 amps, and divide that by our impedance. What is our impedance for this kind of transformer? I said it earlier, it's going to be between 2 and 3%. So let's just use 0.0. I think the one we showed was 2.4%. So push that number divided by 0.024, and we get 1,736 amps. Typically in our homes, we're using 10 KA breakers, so this is well within that range.
That's the fault current. Right there's the fault current in a house. That's in a hall. That's in a home. That'll get you an arc and a spark.
We don't really have it for single phase pole mounted, but he has the nameplate, so it's, as long as you keep it between like 2 and 3%. I missed.
Okay.
Thank you. Yep.
Okay. Got one more.
Now let's take a look at this transformer, or this set of transformers. These are 3-pole mounted transformers. Again, oil filled or liquid filled. These ones happen to have FR3 in them. 25 kVA, that's what the 25 is on there. And actually, if you get up close, and again, if I, up earlier, I was up showing you on from the bridge there. If I looked at that nameplate, I could actually see the nameplate and the impedance of this transformer. In this case, it's 2.4%. What's interesting about pole mounted transformers is they do have a lower impedance. So we made an assumption earlier, if you didn't know the transformer impedance, you could say 5.75%. But in this case, if you don't know the impedance of a pole mounted transformer and you guess that high, guess what you're going to do? You're going to influence your fault current calculation. So it's important that you don't overestimate the impedance of a pole top transformer. And so if I don't know the value, I might even guess 2% for that one. So 2 to 3% is a typical number. Okay, now that we're getting pretty comfortable with these calculations, we're going to throw another little wrench in the plans. We're going to say there's 3 single-phase transformers pole mounted, and those transformers are connected in delta Y, as shown here, delta Y. So this winding corresponds to that one, this one to this one, and this one to that one. Each winding, each transformer is rated 13.8 kV line to line, 277 volt line to neutral. So here's our neutral point on the secondary of the transformers. 480 volt line to line on the secondary. So our difference in our calculation really is we're going to take this 3 times 25 kVA and make it a 75 kVA transformer. There's our square root of 3 and 13.8 kV. That works out to be about 3 amps. So again, even though the wire size could be very, very small, in this case, we only need about 3 amps on the secondary, on the primary. And on the secondary, again, we already know what that's going to be. It's going to be 75 times 1.2, or about 90 amps. So again, we're starting to become more and more comfortable with that. Why is that? Because we're a 480 volt system. Our multiplier on our kVA is about 1.2, so we're at about 90 amps. Okay, now why am I using 13.8 kV? I could use 12.47 kV for medium voltage. I could use 13.2 kV. I could use 13.8. I may even go as high as 34.5 kV for medium voltage, and I might go as low as maybe 4160 volts or 4.16 kV. But anyway, or even 2.4 kV. But the point is, I'm trying to be consistent, so I'm using the 13.8 for this calculation. So again, you can see what our load currents are going to be primary and secondary. Now let's calculate our fault current. So I fault 3-phase on the secondary is going to be 90 amps divided by our impedance. And again, the impedance for these guys is typically pretty small. So we're going to use, the number on the nameplate in this one, 0.24 per unit or 2.4%, and that works out to 3750 amps of fault current.
I missed this, the example 5, it's the 25, make that to a 30, make that, instead of 10, make that a 25, and then instead of going to 15, make it go to 35, something that like that, because I missed that number.
So this transformer
Yeah.
is 750 kVA, delta.
We're gonna stop here. So example 5, it's a 25 kVA, make that a 35 kVA. I missed that one. Everybody got this? Make these changes and go through your calculations and hand that in. Hopefully next Monday, something like that. Okay, and then we'll do the other ones next week. And before you go, let's do this little thing right here, code thing, because I for what it's worth,
Are you gonna be able to post this since you open YouTube?
huh?
Are you gonna be able to post this screen recording since you open? YouTube?
Yeah, I'll post it. Well, no,
Okay, I wasn't sure if they were.
Oh yeah, something, I really don't know, but since I cut it and hacked it, all that kind of stuff, and I talk over it, I think I'm,
I'm half-
I claim ignorance and I claim educators, something, you claim it as a right to just do it as an educator. I really don't know. The answer is if they come around and they say that you can't do this, I'll stop doing it. But, daggone it, starting and stopping and teaching it and all that kind of stuff, changing it around. I I don't think anybody's gonna. I don't think they're gonna harp at it. I hope not. I hope they don't. I hope they don't. Anyway, okay. So let's do this. Does everybody like this kind of approach better? 'Cause I don't know. Honestly, it will take me a long time to get up to speed, and I'll never get up to speed like this guy was. This kind of stuff. So again, you know, not that I don't want to. Just you got the B team. How's that? Okay, EC and M. Quiz number 507. And again, these you should hand in as well. And if we do I don't know what we're going to do for a midterm, but these are live. In other words, these questions would be live. They're just, you may hate me for it, but we got to do something. And this is weekly quiz by Mike Holt, week of September 8th. This is number 507. Portable carnival or circus structures shall be maintained not less than, what do you think? Okay, let's go. What do you think? A, B, C, D, 15 feet or 10 feet or what? Been to the circus lately and measured it and seen what they put it up as? Huh?
I'll put money on 12 and a half.
12 and a half, okay, let's go to 12 and a half, okay. So let's go with 12 and a half. How do you answer this? Okay, so let's go back and see how you answer this. Okay, the correct answer is 15. Okay, so we missed that one. Let's go to the next one. Portable structure shall be maintained less than 15 feet from any overhead. Okay, that's 15 feet. Okay, next one. Requirements of Article 300 are not intended to apply to all conductors that form an exterior part of equipment or listed utilization equipment. I have no idea about this one. Swag, false. Let's go false. Okay, false. Up here.
I think it's just a presentation.
Huh?
I think it's just a presentation. I don't think it's actual interact.
Oh, they are. They're. Okay.
It says slides.
false. I guess that one right. Grounding electrodes of the wire shall be stranded or insulated or bare. Insulated or bare. I think that's any. It can be bare. You can have bare wire. Okay, let's go stranded. Okay, let's go stranded. Any all the above? Okay, let's see what it says. Yep. Okay. Very good.
We got them all right.
Okay. Want to improve your knowledge? Okay. Let's just look at this and see what the next one is. That was all it was? Was it? Let's see what we got. Let's go. Okay, that was it. That was just three
Print out
questions.
slides?
That was all it was.
Oh,
Three
there's
questions.
slide.
I want you to become savvy on the National Electric Code. I don't want you to take it so seriously that no, you can't do that or whatever, because there's usually a way around it. But I want you to at least know that it exists. And if you really want to, get a copy of it just for your own benefit. But you know, you don't carry around with you like a weapon, but you should know a little bit about it. And that's as close to this course as you're gonna get, because they will nail you out in the real world if you don't know this stuff. Somebody come up.
How do you feel about, I think they're called MAD books, MAD, or like the, little pocket and stuff? Uglies. Uglies. How do you feel about those? I mean, like, do those give?
I'm not sure. I'm not gonna try to, yeah, those little guys, yeah, ugly books, they have value. They have value, you know, after a while, you get to the point where you say, heck with it, and you just do what you think is right. I'm not gonna try to, okay, I'll shut this down. You're dismissed. Take care. Have a good day.